Hi.
Let's see. Hi. Let's see who I can get in here. Who I've got in. I got in Catherine, Haley,
Good morning.
Bree, morning, Stephanie. Oops, there's more waiting. Jennifer. Okay. That's Stephanie. You're not in your kitchen anymore.
No, I'm not. I'm out running errands, and it took me a little longer than I expected.
Okay. All right. Well, that's a new one. You can sit around wherever you are and have class. It's a weird world right now.
Yeah, I know, right? Here is some. Yeah, I don't even know how to get here. Yeah.
Okay, guys. Let's see. I see Catherine. I see Bree's name. I see Tori. Haley, Stephanie, Jennifer's there, the big J. That's what our video starts with, by the way, last for yesterday, a big J. So that's where it started recording. All right. Guys, I got a few things I want to announce, but they're important for everybody. So I'm going to wait a couple more minutes to make sure everybody that can get in gets in. Who have I got? Haley, Catherine, Lainey, Bree, Jennifer, Stephanie, Tori is what, do I have more? Doesn't look like I have more right now. Okay. All right, let's see here. So, did everybody that can hear me right now, and if you can, just if you want to answer the question, just unmute and answer it. Did everybody get their quiz back on the business problem? If you gave it to me. If you gave it to me. Everybody got it back. Okay, I see
Yes,
Haley
thank you.
nodding her head. Bree,
Yeah.
okay.
Yes,
Tori,
I got it.
back. Okay. Tori.
So I read the email saying that I had not sent it in,
Yeah.
but I thought that I had accidentally sent in, I thought it was a quiz ahead.
No, well, the last one with that local max and absolute win quiz was the one before this one. Okay, so the one that was actually due Monday, Katie, was on the business applications.
Okay.
Okay, it's we'll talk about the quiz. I'm going to drop 2 or 3 of the lowest quizzes anyway. So just I want to just make sure everybody understands how to work everything on it. Okay, so that's what I want to do first is go over that quiz, which is why I'm asking. And did you copy off, Katie, did you copy off the quiz at all? Do you know what it looks like?
No, I don't think I did that one because I thought I was a step ahead.
Okay.
So I thought.
What happened with you, I think, is you got ahead before the last one you did was ahead of the one that was supposed to be before it. And then there was one after that.
Yeah, I missed that. Yeah.
That's what happened. I think that's what happened. I couldn't quite figure that out either. I kept looking through my emails and thinking, I thought Katie sent me an extra one somewhere, but it turns out to be there were just 2 that were in the wrong order, sort of.
Okay.
Okay, so let me share the screen right now, guys, while we're waiting, and we'll talk about that. We'll talk about that quiz. Okay. All right, there we go. So Brianna's name is on this one because she nicely typed up her quiz for me, and for some reason when she transmitted it to me, it came out entirely blank, and I needed a blank copy of the quiz, so I went and looked for that one. Let me admit somebody, and then we'll go over it, okay? Because there are a couple of things I did want to talk about, and you'll have one really similar to this on your on the next test. So I just want to make sure everybody understands. So let me let's get to that one and talk about it. I sent it back with corrections, but there are some comments I wanted to make on it to make sure everybody understands the things that they did wrong. The other thing I want to comment on is this. When you send me a quiz, please put your name on it, and it can just be your first name and say Math 70 quiz and the date, and then I'll know which one it is. I got into the situation where somebody was sending it to me untitled. Well, I had to kind of look at, I can't remember every time who's is untitled. And then I'd have some that had a string of numbers on them from a scan. And then I'd have some that were an image, that were a photo, and it was like image 2.3896. And so unless I go in and I rename them all myself, I have the potential of getting mixed up. And I got mixed up yesterday because I think I sent Anahi somebody else's quiz, graded quiz, and she let me know, and that was fine, and I'm glad she did. So if that happens, let me know, and I'll send you the right one. Make sure you got a name on it, which makes it easier for me to find. They all go into my Math 70 folder, but that being said, there's like 12 or 13 of those in there, and if I have to go in and rename every one of them, it kind of slows me down, and goodness knows I'm slow enough already right now without anything else. So let's just go over this quickly, and let me point out the mistakes. And the mistakes were kind of typical mistakes, guys. So I want to make sure everybody understands what they did wrong. So on this one right here, I asked you to write a revenue function. We were given this pricing function here, and we know that revenue is X times little p. So that one is just going to be X times 36 minus 4X, and that one's 36X minus 4X squared. So that's what you should have gotten for your revenue function right there, guys. It's very similar to what was on the last test. We didn't do as much with it on the last test, but that's how we find revenue. The profit function, remember, is revenue minus cost. So revenue here is what we just found. So 36X minus 4X squared minus the cost. And here's where several of you made a mistake. You did not put parentheses here, and it caused an error in the profit function. So the cost is 2X squared plus 6, and that doesn't look very good. There's only one parenthesis there. 2X squared plus 6, and if you left the parenthesis off, you missed the sign on 6. The sign on 6 should have been a negative. So when we play this out, it's going to be 36X. So this is the profit, 36X minus 4X squared minus 2X squared is minus 6X squared, and then minus 6. Fortunately, it didn't mess up what you have to do next for the following reason. The next thing we did was asked how many units it would take to maximize profit. Anytime you see maximize a function, guys, the first thing you're going to do is take the derivative. So the derivative here, P prime, was 36 minus 12X, and the derivative of 6 is 0, minus 6 is 0. The derivative of 6 would have also been 0, so you kind of didn't mess yourself up if you made that mistake. I counted off here, and I gave you credit for what you did right after that. But be careful with those parentheses. I'll say it until the day I die, okay? Don't forget your parentheses. And there's an I right there. Okay. So that's what we have to do. And once we find the derivative, I'm having trouble getting somebody in. Hang on a second. There we go. Okay. So once you find the derivative, if you want to maximize it, remember we need to find the critical numbers. So this is the same thing we're doing for graphs, except now it's in the context of this business problem. If I solve that for X, I get X equal 3, okay? I could plug out a 12, and I'll get 3, pull out a 12, and I'll get 12 times 3 minus X. That tells me the critical number is 3. If I want to put it on a number line, now chances are if they ask you to maximize something, you're able to do it, and it will be a maximum. But if you want to test it, let's look at it. If you put in 4, 3 minus 4 is negative, and 12 times the negative is negative, so it's decreasing on that side. If you put in a 2, 12 times 3 minus 2 will be 12 times 1, which is positive. So you'll get a positive on that side. And what you see is increasing, decreasing. Sure enough, you're getting a high point there. So that's exactly what the answer to the question is. You would produce 3 units of whatever this is. Maybe it's something big. Maybe it's an airplane. Maybe it's a tank. I don't know. But you only need to produce 3 of them to maximize your profit. Now, next part. And this is where some people went astray with what they needed to do here. It says, what is the profit at the point where it is maximized? Well, that's like going back to the original function and finding a point on it, okay? So what I've got to do is just find the profit at this value 3. So I need to find capital P of 3. And the original function, and again, here's where this minus 6 made a difference. It'll be 36 times 3 minus 6 times 3 squared minus 6, which is 108, minus 54 minus 6. So that's 108 minus 60, which is $48,000 or dollars or units, whatever. I'll just say dollars there. That's what most everybody did. All right, so $48. If you had had a plus 6 right here, it would have thrown you off by 12 units. It shouldn't have been a plus 6. It should have been a minus 6. So there are 12 units in between minus 6 and 6. You got 60 here if you messed up your profit function up here. Okay. The last thing is what price should be charged to obtain maximum profit. That's asking about price, guys. The price function is this little p right here. So that little p is the price or the demand function. Okay. So what I need is 36 minus 4x. All I need to do is evaluate that thing, little p of 3. It's 36 minus 4 times 3, which is the x where the maximum profit is. And you'll get 24 whatever dollars or whatever. It looks like you're gonna, if you sell 2 of them, it looks like you're gonna maximize your profit. Okay, questions anybody about that one? Is everybody okay on that? If you got you might want to go back and look at your quiz, make sure you correct it. The quizzes, I was gonna tell you, the quiz we've got right now from the beginning of the semester, we have got, let's see how many quizzes we got. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We got 9 quizzes now. We'll have more before the end of the semester. A lot of times I'll give 13 or 14 and I'll take the top 10. Any that you've missed, I will, those will be the ones that you drop. Okay, so I'm not factoring in zeros or whatever. So don't make every effort you can not to miss quizzes. But if you do miss a few, 2 or 3, it's probably not going to hurt you. That being said, if you make a higher grade on a quiz you might have missed than you made before, you know, if you made a 10 instead of a 7, that 10 is going to sort of go in the place of that 7. So just be sure you get the homework in. Plus, it'll help on the test. Okay. All right. Any questions about that? Anybody? Okay.
No, we're good.
Question?
No, you're good. Thank you.
Okay. Okay. Now, let's see. What else did I want to talk about? I didn't realize it. And I was shocked when I looked at my Moodle site today and I saw that I don't think I had this posted there. I think somehow I forgot to post it. I didn't see it. And I might have talked about it, but this was for our week number 3 online. I backed up and put what we did on Thursday, which was concavity. I did more concavity things yesterday, the point of diminishing returns, and I did more curve sketching summary. I assigned a few problems in the book, and then I assigned these problems down here. Now, if you did anybody realize that I didn't put that up there, or did anybody see that? In any case, this is right here, what we had the homework for last night is really important. If you look at it, remember the point of diminishing returns was an inflection point. The curve sketching summary is when we put everything together. The increasing, decreasing, concave up, concave down. These problems right here do that. And I put off making a key for these because I want you to look at these on your own. Do everything for those things. Label all the points. I think I looked at this on the video yesterday, but I just never posted it on Moodle for some reason. Do all those for these. When I give you your review sheet for the test, this is going to be part of the review that we did all these and we looked at, and then I'll give you a few more to practice on. Okay, but this will be a huge chunk of your test where you do all of these things right here. You know, increasing, decreasing, local maxes, local mins, concave up, concave down, inflation points, just on, and then finally get a picture of this thing. We are going to go back to some more graphing techniques too after today. So we still have another whole day on graphing. So if you did not look at this last night, make sure you look at the Monday homework. What I'm doing today is not going to take, well, I don't know, it'll probably take the whole time, but it's not very hard. All right. So, and it sort of leads into something I'm going to do on Wednesday. So start with the Monday night's homework if you haven't looked at that yet. Okay. So there is a quiz due on Thursday. That quiz, I'm going to check, make sure it's on Moodle, but I think it's on Moodle. So it's one of these problems where you go through everything. You find maxes, mins, you try to draw a picture. So that's an important one, guys. Make sure you do that. And as a matter of fact, I'm going to count that one because it has so much to do in it as 2 quizzes. Okay, so I'll just record that grade twice. All right, so be careful on it. Okay, I will check to see if I've got it there. So it's a little bit away. I would like to get it on Thursday by class time, and so I can look at it and get it back to you quickly. Okay. Anybody questions so far? All right, let's look at what I'm going to do today. Today sort of feeds something that I'm going to do tomorrow. And it's a good review of some things we've done. And if you look at what I first got written here, you'll see some things we've already done. I'm giving you a function, and the first thing I'm asking you is, what's its domain? So if you will, tell me, anybody, cut off your mic if you want to talk, tell me, is there a problem with that function anywhere? Is there anything I have to throw out of the domain there? Anybody?
2.
2. I have to throw out 2 because it makes the denominator 0. Okay, so if you remember what we did way back in another time, I don't know when it was, February, we said 2 is an issue there, and the function cannot be 2 because 3 over 0 is undefined. But if you look to the left and the right, all these values are okay. So when we write the domain, we write it in interval notation as minus infinity to 2, union 2 to infinity. Now, I encourage you to look back at the first test. I had some domain problems on the first test, and as I recall, people didn't do that great on it. And then I gave a retest, and the people that did the retest stumbled with this as well, okay? But domain is a set of all values that a function can legally take on. And one of the first places you look is there a place where the denominator could be 0? If so, I have to throw it out. That's the only problem in this function, so that domain is everything but 2. Remember that these parentheses bump out 2. They say we're not going to include 2 on either end. Now, one other thing I want to look at is something that we've already done, or we've done in the past, is limits. And I'm going to look at a limit of a function. And remember what this little minus sign meant and what this little plus sign meant here. This meant the limit as x approaches 2 from the left. And this one meant the limit as x approaches 2 from the right. And one of the things that I did when we first did limits was look at what was happening to a function as we let a value get close to something here. Now note that I'm letting it get close to somewhere where it's undefined. But that's okay. You know, it's not undefined until it's 2. So anything close to 2 is okay to plug in. So if I look at the limit as x approaches 2 from the left, what I did here, guys, was I put the function, and we did some of this back in February. I put this function, 3 over x minus 2, into the calculator, and I plugged in things that were closer to 2 on the left. So for example, if I'm coming in to 2 from the left, if we look back up here, from the left, I'd be coming through values that were a little bit less than 2. So I picked 1.98, 1.99, 1.999. In other words, I'm getting closer to 2 from the left, okay? When I did that, and plugged it in, the values I got for the function were minus infinity, minus 300, minus 3,000. If I went to 1.9999, it would be minus 30,000. What are the numbers doing here? What are the values of the function doing here, guys? What does it look like happening when you go minus 150, minus 300, minus 3,000? Where are those numbers going? Are they getting closer to anything? Anybody? Are they getting closer to anything? I'm not sure they're getting closer to anything at all. What are they doing? They're actually doing what? Getting more and more what? Getting more and more, bigger and bigger negative numbers, right? So what's happening here is that we say that if we come into 2 from the left, the value of this function is just bottoming out. It's going to, minus 3,000, get closer, minus 30,000. And the reason for that is you're dividing by a smaller and smaller number here. If you get closer and closer to 2, for instance, 1.999, it'll be minus 1,000. And when you invert and multiply, the difference between that and 2 will be minus 1,000. When you invert and multiply, you'll get minus 3,000. So if you see what's happening, this thing is actually doing what we say is going to minus infinity. There is nothing to stop it. The closer you get to 2, it just bottoms out. It's just going, the y values are getting less and less, okay? If you look on the right, so in other words, coming in from the right, I'm going to start at 2.1 and look at this. 3 over 2.1 minus 2, we 3 over 0.1. 0.1 is a tenth. When I invert and multiply, I get 30. That's what your calculator will do. If you get a little closer to 2, 2.01, 2.01 minus 2 is 100th. 3 over 100th, invert and multiply is 300. Get closer. Again, I'm plugging it into the function. It'll be 3 over 1,000th. If you invert and multiply, you'll get 3,000. So whereas the one on the left was going to minus infinity, what does it look like the one on the right is doing?
Positive infinity.
Yeah, it's going to positive infinity. Exactly. So what's happening to the function close to 2 is that it's shooting up in one direction and down in the other. So let me give you a definition here, and then I'll show you how that affects the graph. It says if f of x approaches infinity or minus infinity as x approaches c, and c in this case, our case was 2, from the right or the left, then the line x equals c is a vertical asymptote of the graph of the graph of f. I couldn't figure out why I wrote off there, but it's of f. Okay, so graphically, it's not hard to see. If you were to put this on your calculator, here's what you would see. Right at 2, that is not in the domain of the function. So there's no point there. The graph cannot go through 2 because 2 is not in the domain of the function. What happens at that place is that the vertical line x equal 2 is called a vertical asymptote. And what happens as you go to 2 from the left, now that would be from this side, we said it was getting closer and closer to minus infinity. So it's shooting down like that. If we come from the right, it's shooting up because it's going to infinity. But it can never cross, two things. It can never cross this line. And the nature of an asymptote is it either shoots up or it shoots down. Now, some functions might shoot up on both sides, okay? But the point is it never crosses that, and it's either going to infinity or minus infinity. Now, if you have your calculator with you, you could put this in to your calculator, and you'd want to put it in carefully. Let's look at that for a second. We want to put it in pretty carefully, so if we put it in the calculator, we'd put 3 divided by x minus 2 to make sure that we got, whatever the graph was, we got to get those things in parentheses in the bottom. So all of the numerator is divided by x minus 2. If you put it on your calculator, you'll kind of see this happening. You'll see something shooting up and something shooting down. But depending on how your calculator is set, you got to be smarter than your calculator. This thing never crosses that asymptote. Sometimes if you've got your calculator on a particular setting, what happens around an asymptote, this one went down and then went up, your calculator tries to connect it and you'll sort of see something like that. That is really not what's happening. That it is not connected in any way. The calculator tries to do that because it's just looking at a set of points. But if you put it in a different mode, and I don't want to talk about the modes right now, but the idea is around one of those places where the function's undefined, it shoots up, it shoots down, it does not cross that line. So that thing right there, that line right there is really, I dot it. That's what I like to do with it. I dot that line and just say that's the asymptote. And by the way, write it as a vertical line. We know the equation of a vertical line is x equal to a constant, okay? So the interesting thing here, and let me give you one more example so we can talk about it a little further. If you graphed 1 over x, it's clear that the denominator cannot be 0, all right? So the domain is minus infinity to 0, union 0 to infinity. Is there anybody that doesn't understand that? At x is in the denominator down there, it cannot be 0. So x can't be 0 there. So not only is it not in the domain, but the nice thing about this is that the things you have to throw out of the domain are often the asymptotes. As a matter of fact, they're almost always the asymptotes, and I'll tell you when in a second. But so x equals 0 is a vertical asymptote, because if you look at this thing, and I'll put the dotted line right there at x equals 0, if you look at this thing, it has a shape that is getting closer on one side and closer on the other side. Now, let's connect this with some things we already had. I want to try to graph this. Now, I kind of know what it looks like, but I'm also I'm gonna show you something, how it's gonna connect to something I'm gonna do tomorrow. Suppose I wanted to know where this graph was increasing and decreasing. If I wanted to know increasing and decreasing, I would look at the first derivative. Now, if I rewrite this as x to the minus 1, the first derivative is minus 1x to the minus 2, which is minus 1 over x squared. Now, guys, there's no critical number here because there's nowhere where the numerator is 0. There is a place where the denominator is 0, but the function is 0 there too. So what happens there is not really a critical number. It's actually where that asymptote was. And we do need to put asymptotes on the line here because things can change from increasing to decreasing around an asymptote. Now here's how I'm going to test. If I say, let's test something right in this to the right of 0, okay? And again, this is the asymptote x equals 0. And I've run out of whatever. Or that's right there is asymptote x equals 0. But if I test to the 1, if I plug in 2 squared is 4, and I got a minus sign here. That says it is decreasing right there. On the left-hand side, if I plug in a negative number, to the left is 0. That looks like a 1 there, but it's not, guys. To the left is 0, say minus 1. Well, minus 1 squared is positive. So minus 1 over a positive is still minus 1 over a positive is still minus. So it's still decreasing over there. All right, so it's decreasing on the left of the asymptote, and it's decreasing on the right of the asymptote. Now here's the next thing I want to do. If I want to find out about concavity, I'll look at the second derivative. I'm going to do a lot more of this tomorrow, but I just want to touch on it today so we got a little head start tomorrow. if I look at the first derivative, it was minus 1x to the minus 2. The second derivative is the derivative of the first derivative. So I'll get positive 2x to the minus 3. So I get 2 over x cubed. If I were to draw a number line for that, clearly it's not defined as 0, so I've got this asymptote at 0. To the right of 0, say at 5, 2 over 5 cubed is a positive number. That means over there it's concave up. Now remember, I'm looking at the second derivative here. That tells me about concavity. To the left, say at minus 1, a negative number cubed is negative. So negative 1 cubed is negative 1. So 2 over negative 1 is negative, and then it's said to be concave down. So I'm going to try to put all this together, guys, and see what the graph looks like. First derivative tells me increasing and decreasing. In this problem, it said it was decreasing everywhere. Can't cross that asymptote. And it also said that the concavity changed. Now, let me make one small point here. Even though the concavity changes there, it can't be an inflection point because there's no point at that where that asymptote is. So I'll show you there, it doesn't connect. So there's no actual point there where it changes concavity. If I looked at the master line, on either side of the asymptote then, I have decreasing from over here, from the first derivative, concave up. And on the left-hand side, I have decreasing concave down. Now, let's think about the shapes. Decreasing concave down looks like that. Decreasing concave up looks like that. My pen was going down when I drew it. So that's the decreasing part. Bowed downward is concave down. Bowed upward is concave up. What the graph looks like is this. To the left is 0, and that's 0 right there. The shape is caught in between there so that it's dropping down. This is an asymptote. It's dropping down there. And it has to be down in there. There's another reason. We'll talk about that in just a second. This right-hand side is kind of getting closer and closer to that, to the asymptote as it goes up on that side, and looks like that. So that's what that function looks like when we put it all together with the shapes and things we've learned and the increasing, decreasing we've learned. Okay, one other thing here. Let's do one more example. I'll come back to more of that tomorrow. Look at this one. The domain of this function, if I factor this, I see that x can't be 3 because it makes the denominator 0. And x can't be minus 2. I need to factor that to figure that out. So the things I need to throw out of the domain are minus 2 and 3. Those are values where we simply don't have, we can't plug that value in to the function. It makes it undefined. So, so we're doing lots of number lines here for lots of things, but the domain then is minus infinity to minus 2, union minus 2 to 3, union 3 to infinity. Be careful not to leave out the middle part. A lot of people want to leave out the middle part. There's a bunch of points between minus 2 and 3 you can plug in, so those are in the domain too. Now, because the function's undefined there, we're actually going to have asymptotes there. So the asymptotes x equal minus 2 and x equal 3 would run like this. X equal 3 would be right there running through 3. X equal minus 2, that's 3 right there, would be this. So its equation is x equal minus 2. So I have asymptotes, 2 asymptotes here. And again, you find asymptotes essentially the same way you find the domain. You look at where things can't be 0. There's one tiny little exception there that I'll talk about in a minute. Now, I don't know what this graph looks like, guys. I'm going to throw something up there right now because I don't want to go through all the increasing and decreasing, but it could look like this. It could be getting closer on that side It could be looking like that. It could be doing that. But anyway, near these asymptotes, you see what's happening. Things are either shooting up to infinity or down to minus infinity. I can't cross them, and the behavior near them goes out of control. It either goes infinitely up or infinitely down. Questions, anybody? We'll look a lot more at the graph part of this tomorrow. All right, here's one little exception here, guys. You find vertical asymptotes by factoring everything. If something has a common factor in it, this one right here, I mean, you might look at this and say, well, the asymptotes are 2 and minus 2. That's not quite true. If something drops out, and you might remember this happening in finding a limit, if something drops out, in other words, if there's a common factor in the numerator and the denominator, then that actually indicates that there's a hole in the function at 2. That is not an asymptote. If something drops out, it's a hole. I'll sort of draw a picture for you in a second to show you what's happening. The domain on this one is still, x can't be 2, it can't be minus 2. I have to throw that away. We always read the domain from the original function, not after we canceled something, okay? So read it from the original. And the domain then will be minus infinity to minus 2, union minus 2 to 2, union 2 to infinity, okay? Now, the only vertical asymptote here, as again, I said, if something cancels out, what happens there is a hole. The thing that doesn't cancel out here is x equal minus 2. So x equal minus 2 right here is the only asymptote in this problem. Okay, that's the only asymptote right there, x equal minus 2. So that's going through minus 2. Now, what the graph might look like, again, I'm not sure exactly what it looks like. I'm not sure what its behavior is, but I know that somehow it gets closer and closer. It could go up or down. I don't know exactly what it does. But
so what would you do about the hole?
Okay, here, I was just getting ready to tell you that, Haley. Here's what happens with the hole. It gets closer and closer when you're closer and closer to minus 2. But when I get to 2, you've just got a hole in the function, and it goes on and does whatever it's going to do. So I don't know, we don't have, if I put 2 and f of 2 there, there'd be a hole at that spot. Okay, not an asymptote, but a hole. Does that answer your question, Haley?
Yeah.
Okay, all right. So it would be a hole, not an asymptote. Graph would look something funky like that. Okay. So bottom line is, if you want to find, I thought I wrote that down somewhere. Okay, yeah, I did. I go back in my notes, and I did, before I started giving you examples, I said vertical asymptotes happen where the denominator is 0, assuming f of x is a reduced fraction. And what I mean by a reduced fraction is if it had a common factor, you canceled it out. After you canceled it out, the canceling out things will be holes. The things that are left will be asymptotes. So that's the deal right there. Okay, next thing. Not only can functions have vertical asymptotes, but they can have horizontal asymptotes. All right, so the definition of a horizontal asymptote, it says if f is a function and L1 and L2 are real numbers, then the limit as x goes to infinity of a function approaching a constant, and the limit as x goes to minus infinity of a function approaching a constant, are called limits at infinity. The lines y equal L1, sorry, and y equal L2 are horizontal asymptotes. Now, I'm going to look at this, and I think you'll visually see what it is better than from this definition. But basically what it says is if you plug in x is bigger and bigger to the function, and it's getting closer and closer to a single number, we call that a horizontal asymptote. Same thing, if you go to minus infinity. So a lot of books will call this the end behavior of a function. How is it behaving in the end? Is it getting closer and closer to anything in the end of its run? Okay, it's called end behavior. All right, now, one thing I want to show you that's kind of easy to see, and then we'll come back to that definition. If you let x go to infinity, and you're looking at 1 over x to an r value, say maybe 1 over x squared, and you're letting x get bigger and bigger, and that's what this means, x going to infinity, then the denominator of this thing's getting bigger and bigger, and 1 over a bigger and bigger number is going to 0. The denominator is getting bigger and bigger, the numerator is not changing, this thing is getting closer and closer to 0, okay? Same if you go to minus infinity, getting closer and closer to 0. So what we will have here is a line where something's getting closer and closer to 0 as you're going out, infinitely out to the right and infinitely out to the left. All right, now here's what I want us to look at. I don't want to dwell a whole lot on this, but I want to talk to you about how to find horizontal asymptotes of rational functions. And it's really easy to do. If you've got a rational function, now remember what a rational function is. It's one polynomial over another polynomial. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. Now, degree means, guys, the highest power of that polynomial. So look at this problem right here, and I'll just leave the how-to thing up there. If you look at the degree of this thing, what's the highest power of x that appears in that thing right there? Anybody?
Negative 2x.
Well, the power on x, the power on that thing. That's the coefficient. What's the power on x there?
There's not one, or 1.
Yeah, it's 1. It's understood to be 1. Okay, so the degree, we say the degree of that polynomial is 1. Okay? So guys, yeah, when you see an x, it's understood to be 1. What's the degree in the denominator there?
Yeah.
It's 2. All right? I want you to notice that the degree in the denominator is bigger than the degree in the numerator. And basically what that means is that this thing, when you square something, it gets big faster than when you raise it to the first power. So the denominator is getting bigger than the numerator. The bigger x gets, the bigger the denominator gets relative to the numerator. And what that says is we get a smaller and smaller fraction, and that thing has a horizontal asymptote of y equals 0. In other words, my graph might look like this. It might do this, but in the end, look at the end behavior. Look at the tail of the graph here and the tail of the graph there. They're getting closer and closer to this line y equals 0. Okay? So if the numerator is the degree of the numerator is less than the degree of the denominator, we say the denominator is overpowering the numerator and it forces it to 0. You could look, I let you look at that. That's roughly what that's going to look like. But you'll have, and by the way, we don't have any vertical asymptotes because that's never 0. You might think you can factor it, but you can't. If you square something, it's positive, and times 3 is positive. Add another positive, you'll get a positive. You're never going to get any vertical asymptote there. You will get a horizontal one. All right, let me show you. So that's one case. If the degree in the numerator is less than the degree in the denominator. You got this to refer to, so, but it's nice to understand what's happening. The second situation, if the degree of the numerator is equal to the degree of the denominator, then the asymptote y equal a over b is an asymptote where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Now, again, this is pretty easy, guys. If you've got squares both in the top and the bottom, in other words, if the degree in the top is the same as the degree in the bottom, so they're sort of growing relatively at the same rate because of this x square here. the asymptote then becomes dependent on the coefficients of those things, depending on which is smaller or bigger or whatever. Doesn't really matter. It's just that what it says here is if you look at the leading coefficients, now guys, leading coefficients are the coefficients on the highest power term in the polynomial. So the leading coefficient, and this is, Katie, this is where the -2 comes in. The leading coefficient is -2 up the top. The leading coefficient here is 3. And whether they're written in order or not, guys, it's always the coefficient on the highest power of x. So y equal -2/3 is an asymptote for that. Now, I'm not going to go into a lot of detail there about what's going on, but they're growing relatively the same. It's all dependent now on what the coefficients are. So here's what it would look like in a graph, or let me show you what would happen. This line right here, y equal -2/3, is something that the graph of that thing is getting closer and closer to -2/3 as we go to -infinity. So for instance, it might look like that. It gets, let me do this. It gets closer and closer to -2/3 as you go to infinity in one direction and -infinity the other. So again, this horizontal asymptote describes the end behavior. What happens in the end? In the end, the graph tails off in both directions, getting closer and closer to -2/3. By the way, you can cross, it's okay to cross a horizontal asymptote. It's not okay to cross a vertical asymptote. We'll see examples of that later. But it describes what happens in the end. And you always look for power the same here, highest power, degree the same. Pick up the coefficients off these, and that'll be your horizontal asymptote. So the problems on the homework on these shouldn't be too hard. For example, if I say, suppose I give you the function y equal 3x cubed plus 2x minus 1 over 6x cubed minus x plus 3. Notice the powers are the same. Tell me what the horizontal asymptote will be. Anybody? What's the horizontal asymptote going to be?
Maybe 1/2.
1/2. Because, good, because the 3/6 are the coefficients on those highest powers. Y equal 1/2 is going to be my horizontal asymptote. You can look at that and do that in a split second. Not very hard, okay? The final thing about asymptotes is this. What if the degree in the numerator is greater than the degree in the denominator? Then the graph of f has no horizontal asymptote. Look at what happens, guys. Which is getting bigger faster? An x cubed, and I don't care if it's negative or positive, an x cubed or an x squared? Which is getting bigger faster? Anybody?
X cubed.
Yeah, the cubed. So what happens is that the numerator's overpowering the denominator because the power up here is bigger than the power down there. And if it's overpowering, the numerator's overpowering the denominator, this thing just goes on down to wherever, -infinity up to infinity. There's nothing to stop it from getting bigger and bigger or less and less on either end. There is no asymptote there. Okay, so it's not getting closer and closer to any horizontal line. It just keeps falling out because, and going up infinitely because, again, the numerator power is dominating the denominator power. So you got 3 cases. Just to summarize, you got 3 cases. When the power in the numerator is less than the power in the denominator, y equal 0 is a horizontal asymptote. When they are the same, the leading coefficient is the ratio of the leading coefficients is the horizontal asymptote. When the power in the numerator is higher than the power in the denominator, there is no horizontal asymptote. Okay. So one quick thing in my last, however, 1 minute. If it says a small business invests $5,000 in a new product, the product will cost 50 cents per unit to produce. So if I want to write a cost function for that, it would be 0.50x, so 50 cents per unit, plus $5,000 in fixed costs, okay? If I look at that, and again, that's a fixed cost, that's a per unit cost, so that's why I put the X there. The average cost function, I want you to remember, is the cost function divided by the number of things you produce. So it's just C over X. So I put this thing in the numerator and that thing in the denominator. It says what's the limiting value here? In other words, as we go to infinity, is there a horizontal asymptote? Well, let me show you something here. Suppose I said find the average cost of producing 1,000 units. It would be 0.5 times 1,000 plus 5,000 over 1,000. You're averaging out your cost. If you produce 1,000 units, each unit's going to cost $5.50. That's 5 times 1,000, guys. I messed up there. The function was actually 0.5x plus 5,000 over x. So the average cost will be 0.5 times 1,000 plus 5,000 over x. Each item will cost you an average of $5.50. That tells me I probably maybe should just produce more. If I produce 10,000 and I plug in 10,000 for my x and average it out by dividing by 10,000, their average cost has gone down to $1. If I produce 100,000 and I find the average by finding this function right here, the average cost per unit has gone down to 55 cents. This is what are called economies of scale. You want to produce as much as you reasonably can because that way your costs go down because your fixed costs are spread over. This 5,000 is spread over a lot more units. Now, here's the question. Basically what happened here is that I was looking at the limit as x goes to infinity of this function right here, 0.5x plus 5,000 over x. Well, guys, all that is a rational function. And if I want to know what's happening to it to infinity, I'm looking at the asymptote. The power in the numerator is the same as the power in the denominator. And if you look at that, that tells you that y equal 0.5 would be a limiting value. So in other words, you're not going to go any lower on this thing than 50 cents per unit. So the graph might look like something like this, where if that's 50 cents per unit, we're getting closer and closer to that. We're not going to go any lower than that. Okay. I'm looking at the next page, and we're done with time. I don't know what happened on the next page. Oh, I was going to draw a graph. I don't know why it got sideways either. I guess I forgot to turn it around on the scanner. But that's the graph that I just drew right there. It just gets closer and closer to this 50 cent mark right there. And the asymptote is y equal 0.5. The asymptote is y equal 0.5. All right, I wanted to add to your homework, the homework that's on the sheet for tonight, a couple of these problems so you can look at them again, 61 and 63. Okay, so that's added to the sheet on Moodle. Okay, same page, but just a couple more problems. All right, questions, anybody? Okay, we're more than out of time here. I'll post this again. Don't forget, tonight I first want you to look at, we'll deal more with this tomorrow, but I first want you to look at those graphing problems where you're finding increasing, decreasing, all those, and we'll do a few of those tomorrow. And we'll look at the asymptote homework and some more things about asymptotes. Questions, anybody? Michelle, you always look like an angel because got y'all that light behind you. Like you're, never mind, whatever. Okay, I'll talk to you tomorrow. Email me if you have any issues or concerns, and otherwise I'll see you tomorrow.
Thank you.
Okay, bye-bye.